Yeah, so far we have understood addition and multiplication using modular arithmetic. So now we are going to take a look at the exponents, right? The exponent operation. What do they mean? Once again, we are going to take a look at this example using the Z5 set. So there's a Z5 set. Yeah, so these are the elements of that set. So what does this mean? 2 to the power 3. What does this mean? Does that mean 2 plus 2 plus 2 or 2 times 2 times 2? Okay. So we have to be precise. In the definition of the group, we have the set and the operation. So here the operation can be two things, either addition or multiplication. First we will take a look at the addition. Alright. So when we take a look at the addition, if we do 2 to the power 1 will be 2, 2 to the power 2 is 2 plus 2, which is 4, 2 to the power 3 is 4 plus 2. Right, so 4 plus 2 will be 6. Okay, again we are only care about the reminders. And 2 to the power 4, we don't actually have to compute the number 16. Right, think about it. I mean, of course it is very easy to know that, but when we are working with large numbers, when we are writing the code, right, we want to optimize for speed. Okay, so when doing that, we don't actually have to compute the very big number. All we have to do is just do 1 plus 2. We'll still get the same correct remainder. Okay, so that will be 3, and 2 to the power 5 will be what? 3 plus 2 is 5. 5 is 0 because 5 is divisible by 5. Then we get the cycle. 2 to the power 6 is 0 plus 2, which is 2. 2 to the power 7 is 2 plus 2, 4. 2 to the power 8 will be 1. 2 to the power 9 is 3, and 2 to the power 10 will be again 0. Right, so we get this cycle. You can verify that. Okay, let's try to do for 1. So for 1 also, I'm denoting this set 1 power x. Right, so this will be 1, which is 1 power 1, and 1 raised to the power 1, and this is 2, 3, 4, 0. Okay, so this will be 1 power 2, this is 1 power 3, and 1 power 4, and so on. Right, this is 1 power 5. Similarly, you can verify that 3 to the power x, so 3 also generates the entire set. It will be 3, 1, 4, 7. 7 will be 2, right, because you only care about the reminders. And similarly, 4 also will generate the entire set. So it will be 4, 8 will be what? 8 will be 3, and 7 is 2, 1, and 0. Okay, 2 plus 4 is 6. The thing is, we have to notice that this single element 2, it generates all the other elements of the set. Of course, 0 is the identity element under addition, so anything you add to 0, it will still be 0. So except the 0, which is the identity element, that is, except the identity element, every single element of this set generates the entire set. Right, keep this in mind. Alright, now if we take a look at Z5 under multiplication, so 1 is the identity element. So Z5 under multiplication, we don't have the element 0. We only have these 4 elements. Why? Because under multiplication, 1 is the identity element. So if you go and look back at the definition of the group, every single element should have an inverse. Okay, since 0 does not have the inverse under multiplication, it cannot be considered in this group, right? And 1 is the identity element, so anything power 1 will still be 1, doesn't matter. If we take a look at this 2 to the power x, all the powers of 2. Okay, for 2, let me generate. Yeah, we can let's generate. Yeah, let's generate the set. So 2 to the power 1 is 2, 2 to the power 2 is 2 times 2 is 4, right? So 2 to the power 3 will be 8, but we only care about the remainder, which is 3. And 2 to the power 4, we don't have to compute the number 16. We can simply do 3 times 2, which will be 1, because the remainder of 6 is 1, right, when divided by 5. Similarly, 3 power x, we will get 3 to the power 1, 3 to the power 2 will be 9, which is 4, 3 to the power 3 will be 12, right, which is 2, and 3 to the power 4 will be 6, which is 1. So this also generates the entire set. So here we have only 4 elements. But 4 to the power x, this is very interesting. So because 4 to the power 1 is 4, 4 square will be 4 times 4 is 16. 16 gives the remainder 1 when divided by 5. So we get 1. And again, if you multiply 1 with 4, again you will get the element 4. Okay. So in this particular case, 4 did not generate the entire set. So what is the importance of this? The importance of this is that in cryptography, when we are selecting a group for encryption or signature scheme or whatever, we have to make sure that order of the group is a prime number. Right? So here, what is the order of this set? Order of the set means the number of elements in the set. The order of this set is there are only 4 elements, so the order of the set is like order of the Z5 under multiplication is 4. It only has 4 elements. Okay, but order of Z5 under addition, right? So this hash is my way of saying that the number of elements. Okay, under addition is 5, 0, 1, 2, 3 and 4. So 5 is a prime number, and that is why every non-zero element, that is every element which is not an identity, generates the entire group. If you go and read about this SECP 256K1 specification, there will be 2 primes, P and N. So P is used to compute. It is used to compute elliptic curve points, like elliptic curve points and arithmetic, right? So the coordinates, or the operations with x and y coordinates are done using ZP, right? But the order of the group, the generator point, okay, we have this generator point G in the specification. So this G generates a set of elements like G to the power 2, G to the power 3. So here G to the power 3 means it is addition. Here G to the power 3, so in this case G to the power 3, it represents the elliptic curve addition of G plus G plus G. Okay. So yeah, so if we consider the order of this group, that will be N. Okay, so the order of the group is N. So this both P and N are prime. This adds to the security of the scheme, the elliptic curve signature scheme that we are using in Bitcoin.